start this recording. Yeah. Okay, so I hope everybody knows that today's class is online. And if some of your friends contact you, please let them know that it's online on the Zoom link on Blackboard. Okay, so what I want to do today is briefly check how your first submission went for assignment 1, and also pick up a couple of topics from last time, and then talk about today's lecture. So before that, let's talk about assignment 1. Did anybody face any issues with the logistics of it, which is to submit online using Blackboard? No response? Can everybody hear me, by the way?
No problem, sir.
Okay, so I see
Professor,
Avinash
I had
saying
one
yes.
doubt.
Yeah, go ahead.
Like from the 4 people group, like we have submitted 1, that should be fine, right?
Yeah, and so that's why we wanted the groups beforehand, so that we can configure it behind the scenes on Blackboard. Yeah, so 1 submission should be enough. Yes.
Thank you.
Yeah. Okay, so that's good. So okay, so if there is no so nothing to discuss about assignment 1, and we'll discuss assignment 2 now, because it involves CNNs and actually trying to get started with PyTorch and so on. So let me share my screen first. Yeah. Yeah. So just to kind of, this is just logistics. So right now we are on this lecture. So we are in lecture number 4. It's mostly going to be, as you'll see, about introduction to NLP and getting a feel for what I call word embeddings at the end of the day. But we have a couple of topics from last time that I want to first, cover. One of them is dropout, and the second one is just go over an example CNN code. Okay, so we will kind of revisit that and get a feel for PyTorch code in general. Okay, and I know some of you have offline discussed with me a little bit about PyTorch, so maybe we can look at what are the pain points, or what are some conceptual hurdles that we should kind of know about and then work through, right? So let's actually, as I said, today's objective is start looking at text and how to process text. So all the ideas that you know from before are a good set of tools to work with, like TF-IDF or bag of words and so on. But today we'll be talking about word embeddings. Okay, and so we'll talk about, just like image embeddings were representations of images as vectors when you pass through a pre-trained network, word embeddings have are a similar idea. So each word will have a vector representation. Okay, and so that's the goal for today. And I'll show you the lecture goals in a second. But one thing we left last time is dropout, and we'll talk about that. So let me actually switch over to the lecture goals. Oh. Yeah, so from last lecture, one of the goals that we did not get a chance to spend some time on is called dropout. And it works as a regularization technique, very similar to L2 regularization or L1 regularization on weights that we generally do. So we'll discuss that. So one goal today is to kind of know what is dropout, and maybe even use it in some of the networks that you'll design in the assignments or in your projects. Okay, and then today's objective is to understand how natural language elements are processed in a data science workflow, which is, how do you deal with words, sentences, how to do pre-processing. Although we won't spend too much time on pre-processing, but, it's something that you will have to do if you work with text data. And we will be working with text data in assignment 3. Today, we'll also cover some of the more, I would say, simpler models. One of them is naive Bayes model for classification. And then a model that some of you may have seen or may not have seen, it's called latent digital allocation. Okay, so it is a model for doing unsupervised clustering of documents in a sense. Okay, it's called topic modeling. So it's an unsupervised technique, but it's good to know about that. And then we'll look at how the CNN model, CNN network architecture that we learned for images can also be used for processing, can also be used for text classification problem. Okay, and in particular, we'll look at sentence classification or basically sentiment analysis. It's a kind of similar problems. So we'll see how to use a CNN for that task. And you will, so it's not just application of CNN, there's going to be some change. And so that will further reinforce or improve your understanding of convolution operation and in general, such a network architecture. Okay. And the key idea, which is the last goal here, is to really understand this one particular implementation called Word2Vec. But through that, we'll understand how vectorization of words helps in a very similar way how transfer learning was discussed for images. Okay, so once you can get vector representations for words, for example, these vector representations, like there's one vector for let's say word understand, there's one vector for word language. Then once you have these vector representations, your problem is completely numeric. And so a problem is completely numeric in the sense that you have now numbers to work with. And so you can always apply any feed-forward neural network and things like that. Okay, so we'll talk about how do you get those vector representations and why do they make sense. Okay, so those are the goals. So any questions about what we want to achieve today? As I said, to summarize, look at dropout and look at CNN example PyTorch code, and then get started on basics of NLP, its applications, some basic models, including how to use the CNN, and then finally how to represent words. Okay, so that's the summary of the overarching things that we want to cover and understand today. If you have any questions, you can raise hand or use chat, or you can use also your audio. Okay, so let me actually so I want to briefly get a sense of kind of recap what we did last time. Not really recap, but just mention the context in which I'm going to discuss dropout. If you remember last lecture, this was the outline. We continued our discussion with discussion of the CNN architecture. Then we talked about several ways of debugging a pre-trained model, like for example, look at weights, look at activations, use occlusion to understand whether the right object is being detected. So if the object that you want to classify as is occluded, as in covered up, then hopefully a probability of that class is, goes down, which means that you are actually picking up that signal. And for example, also projecting down the image embeddings down to 2 dimensions and seeing whether similar images are project down to the same region of a 2D space. So those were all ideas that were ways to kind of understand this, very, I would say, complicated supervised learning model, right? So next we looked at transfer learning. So how to use a pre-trained CNN, in general CNN, although transfer learning is applicable in general, like even with feed-forward neural networks, it really makes sense for convolutional neural networks because it has that layer-wise property of picking up some lower level features first, and then maybe later layers pick up higher level features. And we looked at 2 types of transfer learning. One is just use the pre-trained model as a fixed feature extractor. And the second version was when you could use the pre-trained model, but then change the model definition so that you can add a couple of more fully connected layers or whatever layers you want, and then do a backprop operation on this augmented network, of course. But then you do that backprop with such low values of step sizes or basically learning rates, so that you only perturb the weights of for example, the pre-trained layers slightly. So that's basically fine tuning those weights, okay, to slightly adapt it to your application. Whereas the new layers that you added, their weights might be random, and so there you can have higher learning rates or higher step sizes, and so that you can learn good weights there. Whereas the weights that you have already learned from the pre-trained from weights that are already learned and exist in the pre-trained network, those you want to slightly change, and hopefully don't change them too much, because they have already been optimized on maybe a larger corpus than what you have. Okay, so that's what we did with transfer learning. And then neural network training tricks, we saw 3 of them. One of them was more about data augmentation. Really makes sense for images. You can crop images, you can slightly change the colors, or you can share the images, or, you can rotate and so on, potentially. I mean, not always, but you can do those things and augment your data. So the same label, for example, the same class, but you have a slightly different image. Okay, so that kind of increases your data set size, and hopefully also makes your network learn well. The other 2 ideas that we saw, one of them was it's not really an idea, but a consideration, which was about weight initialization. There are a couple of weight initialization heuristics that were popular a few years ago that can be used. We didn't mention them, but in the lecture notes, but you can easily get a sense of them. For example, PyTorch implements a couple of these initialization ideas. PyTorch is a software package. It's also true in TensorFlow and so on. So it's the consideration is that where you initialize influences where you get to in terms of the optimized weights that you eventually learn after a bunch of training. Okay, and so one simple crude trick, for example, is to initialize at several different with several different weight parameters and train multiple models, and maybe take a majority vote or average across them, for example. Okay, and this is important because, as I was mentioning before, the loss function as a function of these weights, first of all, the weights themselves are in maybe millions of parameters, okay, million dimensional space. And the loss function, you can't really imagine in a million dimensional space, but if you really think of a 1 or 2 or 3 dimensional space, 2-dimensional space, let's say, the loss function is like has lots of valleys and peaks. Okay, and so when you do loss minimization, you want to get to a good valley. So you want to get to the bottom of all, the deepest valley, but then that's hard typically. And so weight initialization is kind of important in that sense. Okay, and this is even beyond all the other choices that we've done. For example, nonlinearity influences how the gradients flow from back and forth, and that also influences how well you can train and whether gradients do propagate or not. For example, we discussed that when we talked about sigmoid versus ReLU. Batch normalization was another idea, where the point was, if you have a layered structure in your neural network, then what you want to do is the activation statistics. When I say activation statistics, think of training data. Let's say you have 1,000 training examples, then each example kind of will generate an activation vector, let's say, or an activation tensor if you want, but let's say activation vector. Then if you pass each of the training data point, then you'll get maybe 1,000 activation vectors. So if you think of the statistics in the sense that you have these, 1,000 vectors per dimension, if you look at, whether what are the means and what are the standard deviations, you want them to be kind of normalized. Okay, and that's the idea of batch normalization, to kind of ensure that these activations themselves are further processed such that before passing on to the next layer, they are, for example, mean 0 and standard deviation of 1, for example. You want to kind of normalize them, and that's the idea here. And that why do we want to do that is because numbers can keep on compounding and then explode. For example, if the numbers are not centered, for example, one very raw example is if the numbers are all negative, then they kind of severely influence. For example, the ReLUs may be dead. Okay, the ReLU nonlinearity may make the output of the subsequent layers 0 because the input is 0. Okay, input is 0 and weights are positive. Sorry, inputs are negative and let's say weights are positive, then the inner product is going to be negative. And then if you do a ReLU operation, you'll get 0 at the output, right? So anyway, the key idea is to recenter these activation numbers so that they are within a nice range, and so that influences how gradients also propagate back all the way from 10th layer all the way to the first layer, for example. Okay, So that's the idea of batch normalization. It improves and stabilizes training, okay, informally speaking. So what we'll see today is dropout. And so let me get to those slides. So any questions about the overall context? Okay, if you have any questions, certainly drop it in the chat. If something occurs to you later. So in the meantime, I want to talk about dropout. Okay, so dropout is yet another idea. Of course, it's weight initialization / batch normalization / data augmentation. They're all very different from each other. They're not kind of related to each other as such. Similarly, dropout is not related to the previous concepts, but it is an interesting implementation. It's already implemented in popular packages like PyTorch and TensorFlow. So the idea is to make your network more resilient, more robust. Okay, and that's the purpose of regularization. So regularization is all about not building a model completely dependent on data, but kind of impose your preference. Hey, only some of the weights should be positive, and that's L1 penalty in an lasso or an L1 regularized regression setting. Similarly, L2 regularization says, hey, the weights of my linear model, for example, should not be too large. Similarly, dropout also kind of serves that purpose of, hey, you want the model to be not overfitting completely to the data. Kind of don't be completely biased or don't build a model that's completely truthful to the data, but introduce your preference. Okay, introduce your regularization. Okay, and what is the regularization? The idea is that we define a network. Okay, so we define a network. We're going to slightly modify the network forward pass. Okay, forward pass in the sense that we have network. When we define a network, just think of layers. Layer 1 is a con layer. Layer 2 is some pool. Layer 3 is batch norm. For example, layer 4 is a fully connected layer, and so on. So you have defined these layers. Now what you're going to do is add an extra processing step, just like batch normalization, an extra processing step between layers. Okay. So what does the extra processing step do? Its objective is to force set the output of a few of the neurons to 0. Okay, set the output of a few of the neurons to 0 with some probability. So it's a processing step. Okay, where let's say you produce the activation vector, or for simplicity, let's talk about vectors, but you can think of tensors as well if you want. So let's say okay, in this illustration, actually, the input. Okay, yeah. So in this illustration, let's say on the left-hand side, you're seeing the usual network. So 3 inputs, 4 hidden units in 1 hidden layer, and then 2 outputs. Okay, so this is the usual operation. So what we're going to do is, once we compute the hidden vector or the activation, okay, and so there will be 4 outputs, right? 4 outputs because there are 4 neurons in this illustration. What we're going to do is for each of the neuron, we're going to flip a coin with some bias and say, hey, if it lands heads, I'm going to just set the output of this neuron to 0, irrespective of whatever its output was before. Okay, so it produced some output, maybe a number 1.1. But then what you do is flip a coin, and if it lands heads, you say, hey, forget about 1.1, I'm going to pass 0 forward. Okay, if it lands tails, then I'll say, hey, I'm not going to do anything. Whatever the neuron produced, I'm going to pass it forward. Okay, so it's just modulating the output of your neurons. Okay, so here you can see in the right hand side illustration, I'm just showing that 2 of the neurons happen to have which are kind of deleted here, happen to have got dropped out. Basically, the neurons got dropped out, and so though their outputs, these dangling edges that you can see towards the output, they're 0, which means that they don't exist because they don't add anything to the output. Okay, so which means that in the right hand side at this point, because in this forward pass those 2 neurons dropped out, the neuron 1 and neuron 3, only neuron 2 and neuron 4 are supposed to produce appropriate activation values such that the output is still such that the score, for example, let's say the score should for class 1. So let's say the top output is for a score for class 1, and second output is for class 2. Let's say this input was to predict class 1 in that training example. Even though I dropped out neuron 1 and 3, the other 2 neurons should still produce some number such that the class 1's score is still high. Okay, so we will do that, right? Because we dropped out these neurons, then we're going to penalize if the class 1 score is still not high, okay, because even if they drop these neurons, okay. So we are basically introducing resiliency. Even if some neurons are off, as in like deleted, the network should still be able to predict your appropriate class. Okay, so in that sense, we're kind of reducing the capacity of the network. Okay, so capacity in the sense how rich of a function you can represent using the neural network kind of decreases, because even if some neurons are dropped, you still need to predict well, which means that there has to be some redundant capacity, redundant robustness in that network, which means that it's not going to be very rich. It's not going to be completely adapted to the training data. Okay. So that's what's written here. So basically make use of the smaller capacity of the network to make a prediction. Okay. So you can think of this as regularization, because you're reducing. So regularization, by the way, is all about reducing your search space, or basically reducing the capacity of your models. Okay. So without regularization, the model can fit whatever data, but if you add regularization, it does influence how much it can fit. It will not be able to fit completely to the data. Okay. That's the idea of regularization, and that's what's happening here. Okay. So in a sense, basically, we're forcing all neurons to be useful. And so here, what I showed is for one pass, right? So for one input, maybe the first neuron and third neuron got dropped out, and you still want to predict class 1. But for the next input, again, you will flip coins, and maybe some other neurons got dropped out and still need to produce whatever the class for that example is, and similarly and so on. Okay, so every forward pass, you're flipping coins, and you're kind of looking at a reduced network and still trying to predict the class of that training example. Okay. Yeah, so as I said, we're basically subsampling a part of the network, in the sense that if you think of a graph, you're dropping some neurons, and so it looks like a kind of a smaller network, okay, which has the original networks, but some parts are kind of deleted, removed. So a perspective that you can take is we're basically getting an ensemble of neural networks. So every forward pass, we're getting a different neural network, essentially, because the connections are slightly different, or some connections are dropped from the original reference network. And so you have all these different networks trying to kind of do well on the training data, okay, right, informally. And so you can think of this as like an ensemble of neural networks that share parameters, okay, because in each pass, it's a slightly different network, but they all have, wherever at least they're common, it's the same weights, right? Yeah, Savinash, yeah.
We are not training this model again. We're simply turning some of the neurons off and running it for different random cases, right?
No, so this regularization is happening while training the model. So think of, let's say we only have 1,000 examples, and we have this exact network. Okay, so one hidden layer. What we're trying to do is, so we have 1,000 examples. Let's say we're doing let's say we're doing a gradient descent. Okay. And let's say we're doing stochastic gradient descent, okay, or batch gradient descent, where we're picking a small batch and then only doing forward pass on that and computing gradient of the loss with respect to the weights and updating the weights, right? So when we do that forward pass, we are dropping some of these neurons, okay, dropping the outputs of some of these neurons. So it is during training that you're introducing this dropout layer in some sense, okay. We'll talk about what we can do at test time in a second, but okay. This is during training, and in fact, I'll show you a code where we'll do this when we look at an example CNN code in a second.
Okay.
Yes, Juan.
Yeah, so just a couple of questions. So you're saying that the backpropagation process just happens as usual, like we update every weight except for the neuron we just
so just think of the reduced network as just as kind of resembles another computational graph, right? Sure, there may be some weights that are kind of gone because they're not even anywhere in the network anymore, but those we can't help. But at least the weights that are still relevant once you have this smaller graph, those weights is just like a regular backprop operation on that smaller graph, right?
Okay. And is there a guideline or a limit about what proportion of the neurons on a given layer we can set to zero?
Good questions. I think, folks, let me just try to see if there's a definition of the network here. yeah, sorry, it's so I'm going to talk about this in a second, but let me, oh, not here. Okay, this is fine tuning, so this doesn't have the network. Actually, trying to remember if there was a batch norm. It's an overfitting example. So give me 1 second. If I have that example, I'll try to find it. Not this one. Not NLP. Maybe, yeah. So let me come to, I'm just going to show, I mean, I don't want to confuse anybody here, except I want to show you how this dropout is added. So since some of you have done, I mean, most of you have done assignment 1, so at least if you are a little bit familiar with how Keras models are defined. And so you can see that you have a regular layer, I mean, dense layer. And then you have a layer with dropout, and there's a parameter. Okay, this is the probability with which you can drop the neurons of this previous layer. Okay, so now this number 0.5, is there a recommendation of what this should be? The intuition is that the higher this number, the lesser the capacity of the network to kind of do well on the training data. So you're going to increase your training error if you have a higher number here. Okay, so instead of 0.5, it's like 0.9. Then you're really dropping most of the weights. And so still the network has to kind of predict well. And so it really regularizes very strongly if this dropout parameter, which is the probability with which to drop out, is high. Okay, if it's too low, like for example 0, it's ineffective. If it's 0, it's ineffective, right? So what is the recommendation for this number? There's no set choice, at least as far as I know. Yeah, this is something to be tried out, very similar to some of these other choices that you have to try, like learning rates and so on. Yeah. Sorry, that was a long-winded answer, but this is an example called overfitting underscore regularization underscore dropout example in the examples folder under NLP. Okay. It's NLP only because it's doing sentence classification, I believe, here, and so that's why it is it's a movie review classification, and that's why it is under this folder. But this is how you define dropout, and it's very similar in PyTorch as well. Okay.
Is 0.5 like standard value, or?
It's here they just chose 0.5. I've seen numbers, range all over the place, like anything like 0.2. Sometimes, generally, people don't drop out too much, so you may not see like high numbers. So by the way, dropping out range has to be between 0 to 1, because that's the probability with which you will delete those neurons. Generally, I've seen numbers like typically between 0.1 to 0.5. 0.5 seems to be on the higher end, actually, but yeah. But there's no recommendation, at least from my end. Yeah. So there's a question, Zoe, which is, does the output of the dropout layer depend on which neurons get omitted? Yeah, so dropout is just setting. So if you think of a vector with 10 numbers, let's say that's the activation vector. It's just that whatever is the activation vector, there's the input. Some of those numbers will be 0. It's the same vector length, except some coordinates will be set explicitly to 0, whatever the previous number was. Okay, and how will they be set to 0? You flip a coin with this bias and set them to 0. And then that vector will be passed forward to the next layer. So if dropout was not there, the original vector, 10-dimensional vector, let's say, was just passed forward to the next layer. If because of dropout, that original 10-dimensional vector, some coordinates will be set explicitly to 0, and then that will be passed forward. Okay, and because they're set explicitly to 0, they don't affect any other future computation, because any further computation with it, it doesn't change anything, right? That's how it is. So it doesn't really change much. So the wiring of the network, wiring of the layers is as if you didn't introduce dropout. You just dropout just sets some numbers to 0. Okay, and so this is during so in the model definition itself, dropout is there. So now you can imagine while doing backprop, you will basically take into account dropout while updating the weights. Okay. Any other question?
Yeah, yes. So
yeah,
like in this case, in this code we are looking at right now, the dropout is being performed on the layer that's defined just before, right?
Yes.
So we do it just once on each layer, but as I understood from the slides, we can do it several times per layer.
In the slide, the example only has one hidden layer, so that's why we only did it once. But in that example, since there are two dense layers or two linear layers, basically it's being done twice. But you don't have to do it. So it's don't have to do
I mean, doing it more than once on a single layer.
No, it doesn't make sense, right? I mean,
okay.
Yeah, if you do it twice, it's basically, you can reduce it to 1, right? So if you have to drop it with 0.5 and then again drop it with 0.5, that's like that's not exactly a multiplication operation, but instead of that, you could have a single dropout layer with a slightly higher chance of dropping.
Okay. Yeah. Okay. Thank you.
So if you want the exact number, it's like 1 minus 0.5 square. Okay, that's the number that you can plug in once, and that should be the same as writing 2 dropout layers. Okay.
Okay.
Yeah. Okay, so I guess my intention was not so much to focus on the code here, but I just wanted to kind of quickly, show an example of how it's implemented. It's all implemented in, as I said, in these packages. But you want to know what its effect is. It's basically trying to set some of the entries to 0, whose influence is. The point is, if you set it to 0, then that it's not affecting the output and it's not influencing the outcomes in the future, like whatever representations and whatever final scores they are, they're not taking that into account, that neuron's output into account at all. Okay, that's what is happening, right? That's how you're building redundancy into the network. Or basically reducing the capacity of the network to represent functions, so you're not overfitting. Okay, that's why its effect is basically regularization. So I guess one final point is about what happens at test time, right? So the model has now dropout parameters. At test time, should we even be dropping out? Okay, so we'll drop out. So there's a question before what I discussed about testing, so which is whether dropout affects training time. It does not, right? So it's basically setting some entries to 0. So it's not really a complex operation. It's like there's no complex operation. Like bash norm, for example, could increase the training time in the sense that you have to do summation and division and produce a new vector. Here also you're producing a new activation vector, but it's a pretty, I would say, simple enough operation that as long as the packages track the new computational graph and know that because of some zeros, the computational graph is simple, it should not affect training time. Okay. So anyway, this is at the conceptual level. If you really care about the implementation detail, then we have to talk about the specific package and how they work with dropout. Okay. And in fact, one of the comments is in this slide, which is how do packages deal with dropout while testing, or once a model is already developed. If you define a model and the model has dropout in it, okay, and then you learn all the weights, and then you have this trained model. Now, for a new unseen example, okay, image or a vector, you want to make a prediction. Then what do you do? So at test time, for example, if you ignore the dropout, then your predictions will be completely off. Okay, so you do want to consider the effect of dropout while making the while making a prediction. So what do you do? For example, instead of doing many forward passes, which is what you would do, right? So you could forward pass with the same input, but do a forward pass, do some dropout, see the prediction. Again, take the same input, do another forward pass, but again do dropout and see what the output is, and then you can aggregate the predicted classes. Take a majority vote, for example. You can do that, but you can also do another thing, which is do a single forward pass. Don't do dropout, but you have to scale the activations by the probability of the dropout. Okay, so here, what do I mean by that? So if you look at here, so at test time, if you don't have if you don't want to do multiple passes, then what you need to do is whatever vector you got here, it has to be scaled down. Okay, so it has to be, whatever the number, let's say the vector is 10 dimensional and it has a bunch of numbers, you want to multiply it with 0.5. Okay, it's like an effect of, it's as if, it's basically scaling down this vector while passing it forward to the next vector. There's a next layer. Okay, so that's what it effectively amounts to. If you want to do that, okay, which is what's shown here in this example. So let's say the dropout probability is P, and let's say we have a single hidden layer neural network. So you have you have some transformation, and then you have a ReLU. This is that hidden layer, and then you are doing a linear transformation to get to outputs. So here, if there was a dropout while training, then what you do is you multiply with P, okay, at test time, and then you get the scores, and then you take the softmax to get the probabilities, and you can predict one of the classes, okay? Or you can directly tell from scores as well. But so you introduce P here. Okay, so that's and this is something that these packages do behind the scenes for you automatically. Okay, so if you have dropout in your network, then you don't have to explicitly do an explicit multiplication like this. The package will directly do it for, like, for example, Keras will do it for you. Okay, if it sees there's dropout in the network definition. Any other question? Okay, so that was about dropout. So it's basically an idea which, again, it's a very interesting idea, a very different type of regularization, and seems to have helped with neural network training. Okay, it's unclear whether it's still, it's absolutely essential for training neural networks, but it's a nice empirical, mechanism that people figured out as a way to train and regularize neural networks in the past, in the past decade. And so it's implemented in most, all the popular packages. So it's worth introducing it in case you think you want finer control on, hey, it's overfitting to data, test error is too high, training error is too low. Let's regularize, and so maybe this is one choice that you can try out. Okay. Okay, so we will switch context now, which is not directly NLP yet, but I want to quickly talk about the CNN. So I want to talk about a specific example that's there in the examples folder. Okay, so it's example/CNN/connet classifier example. The reason I want to talk about it today is because now we'll get into the mode for assignment 2. Assignment 2 has a couple of questions. So one of the questions is about working with CIFAR10 and doing transfer learning. Okay, so this example code will help you at least understand the scaffolding as in a template of a PyTorch vision related training script. Okay. So if you look at it, it's using not just Torch, but also a related module called Torch Vision. Torch Vision has a couple of interesting, Torch Vision has actually a couple of interesting functionality as well as pre-trained models available. And particularly, we will be using one of the pre-trained models, ResNet 18, I believe. And the functionality is the definition of these objects called datasets and transforms. Okay, so if you remember data augmentation, they're basically transformations of the original input images, right? So they're basically you want to crop an image, take some arbitrary square from an image, or rotate an image and so on. Those are all transformations on images. Okay, so Torch Vision provides a nice functionality for you to define those transformations. It also lets you define a nice object which can hold references to where your images are instead of reading all the images into memory. Okay, so if you remember, images are tensors, and imagine having thousands of images into the computer memory or even the GPU memory. It's not an ideal thing to do because they consume a lot of memory. Okay, so dataset object lets you kind of define that, hey, image 1 is at this location, image 2 is at this location, and so on. And so that you can, when you actually do the backprop, when you actually define, get a batch and want to do a forward pass, that's when you read it from disk and load it into memory. Okay, so it helps you with that as well. It helps you with that. Okay, so so what I wanted, the reason why I'm trying to kind of briefly mention this code is not that I want to spend a lot of time going through each and every cell, but I strongly suggest this is a good week to get started on looking at this example notebook, open it in Colab. You will have to change the reference to the location of this data. You can save it in Google Drive, and you can reference it just like we saw with the linear classifier example. So you just have to do a couple of changes in, so that you have to mount your drive so that you can actually access the data. So this CNN example is to distinguish between ants and bees. Okay, so it's just a 2-class classification problem, 2-class image classification problem. Your assignment has a 10-class classification problem. So there'll be some change in the network architecture. Certainly the output cannot have 2 outputs. It has to have 10 outputs, right? And so starting from this notebook, or understanding this notebook, each cell, what's going on, and then modifying it for the for assignment 1, question 1, would be a good approach. Okay, so I want to highlight a couple of things as and not spend too much time on each cell in this notebook. Transforms. Okay, this is exactly the transforms object that was imported. So you can say, hey, randomly resize, randomly flip horizontally, and this normalizes to change the change the median numbers in the so change the statistics of the numbers in the tensor. Okay, so why for example, why this step is to kind of get the statistics of your data set similar to the statistics of ImageNet. Okay, so that's another correction that you can do, not correction, but another operation that you can do. Okay, but these are the things that we have already discussed last time, which is resize or flip. There are many other things that you can do. Okay, if you look at the documentation, you will see that this has a lot of things that you can define. So if you define those transformations, and so here's where you're creating the data sets object. Okay, so it's just saying, hey, here images are in some folder. Okay, while reading the images, you can apply these transformations. Okay, so we're not applying it. It's a lazy approach. So we are just saying we are just defining the data sets object, which remembers, hey, here are the files. And when I read these files, for example, to create my batch, I'm going to apply these transformations and then give it to the model for a forward pass. Okay. Given the data sets, you can also define what are called data loaders. Their objective is their objective is basically to create a batch. So if you have 1,000 examples, the objective of data loader is to say, hey, the data loader is an object which says, which lets you, pick, hey, give me 100 examples. It'll pick 100 examples from there and just give it to you, right? So it's just a way to subsample from your original, let's say, 1,000 example data set. Okay. So, and these are some helper functions. IMShow is to kind of show some images in your data. I think there's a subpart in your assignment which requires you to do this. And here's a training loop, right? So training loop, I won't point out everything, but you can see a couple of things. Not this. Yeah. So you set the current gradients to 0 of the parameters. Then you pass the data through the model. Okay, so we're going to look at the model definition. In a second. I mean, we'll not see the model definition completely because we are actually picking up a pre-trained model. Produce some outputs. Okay, from the outputs we compare it with labels and define the loss. Okay, now the loss is a function of all these parameters, right? Given that specific input that we gave. Now loss.backward computes the gradients, and optimizer the step does that gradient descent step. Okay, so it depends on what optimizer you choose here. Where is the definition of optimizer? So optimizer is passed as input, and so it need not be exactly stochastic. The gradient descent example or gradient descent slide that we had from previous lectures. It could be different. Okay, but it's just going to be a gradient descent style approach. Okay. Yeah, those are the key steps. Everything else is just keeping track of some statistics and just printing them out and so on. So yeah, and there are some helper functions to see things. So I will probably not, yeah. So here we are actually using SGD stochastic gradient descent optimizer, but you could change it to something else also. So for all this, you'll have to look at the documentation. You don't have to change this for your question unless explicitly asked for assignment question. But I would suggest looking at each cell, understanding what's going on. Hey, how is the training function defined, right? So train model function defined. It takes model as an input. What's the loss criteria, or what's the optimizer, and does a iteration, which is an iteration over epochs. And so understanding this loop is going to be helpful, because you will see that almost all supervised learning training for deep learning models will follow very similar template. Okay, so if you learn once, which is the big step, after that, all of them will be having a very similar template, a very similar way of defining things. Okay, it's like scikit-learn's scale, or sorry, scikit-learn's fit predict type of pattern. Here also it's very similar. Okay? It's not exactly fit predict, but you have to but you'll see that template is going to be very similar. Any questions about this part? Okay, and data loaders that I was mentioning. So data sets and data loaders are the new things that you might not have seen before. So it's something that you want to try out. Once they're defined, ignore the whole training loop. You can just try to see, run this for loop separately, maybe outside, to get a feel for what is it that the data loader is producing. Okay, to get a feel for how do you get a batch, a small batch of images from whole collection of images every time you call data loader. Okay, so here the code is a little bit, has one more complexity, which is data loaders is a dictionary which has 2 data loaders in there, one for training and one for evaluation. But it's worth trying out. Okay, so try it in collab and set up the data set so that you can try out this example, and then you'll be more confident in solving assignment question number 1. And question 2 is actually much simpler. It's just defining a custom loss function and doing gradient descent with respect to the appropriate parameters. Okay. Any questions or comments here? Load each batch to GPU/CPU where the model is being trained. Yes, exactly. So it gives you. So it's just think of data loaders as like a iterator. It's an iterator, right? So just like in Python, in regular Python, if you say, hey, for x in some iterator, like a range 0 to 10 or something, so it's going to produce one element or whatever you want from that iterator. And then in the next couple of lines, we are actually sending it to GPU. So when you load it, it's in the CPU RAM, as in it's in the regular RAM of the machine. And then to device, if the device is basically CUDA or whatever GPU, then it's this red image and label is sent to the GPU side. Model is already sent to GPU somewhere, I believe. If not, it must be outside, but model is also on the device. So to device basically is trying to send everything to the GPU so that everything is on the GPU, resides on the GPU, the weights and the data, so that the gradient descent steps happen in the GPU. Yeah. So data loader is just loading. It's like a, for X in range XYZ, right? So, or for X in a list, right? So that's all it's doing, but it's just doing it instead of you writing it in a explicitly, right? You can always do that, right? So if you have 1,000 examples, you can say, hey, first give me the first 10 examples, next give me the 11th, 20th example, next give me the 21st to 30th example, and so on. You can write it, but it just makes it easier. Okay. So it's not complicated. It's just a particular pattern that these folks in, for example, PyTorch and TensorFlow have adopted. And so it's good to know that when dealing with non-structured data, right? So here, data is not read into memory a priori, okay, like tabular data. Even tabular data, if it's too large, you generally don't want to read everything into memory, right? So for example, with pandas, you would do pandas chunking, which is like, hey, read the first 10,000 rows and then let's process it. And then maybe read the next 10,000 rows and process it and so on, right? So it's a similar idea here. Okay, so then let me come back to what our objective for today is. As I said, we're just going to motivate NLP. I think most of you may take a special course in natural language processing, or maybe taking currently, or might have taken already. So it's a good recap for you. What we look at is, we'll start with some applications of NLP, like just motivation, then look at some models that you may or may not have come across. Naive-Bayes, maybe many of you must have seen before. The couple of models just to get a feel for how do you work with words, okay? And you'll see that these models don't really look at the meanings of the words or similarities between words really well. And so that's where we now start moving towards a better modeling approach, and that involves, CNN is one more model that you can look at, but better modeling approach involves representing words such that the vector representations for the word, let's say cat, and the vector representations for the word dog, hopefully those vectors are kind of close to each other, let's say in Euclidean distance, compared to vector representation for a cat versus a vector representation for an aeroplane. Okay, so those maybe they should not be ideally similar to each other, okay, in terms of like some similarity between the vectors. So that's the whole idea of vector representation of words. And once you have these vector representations, you can actually use them just as feature vectors in any downstream machine learning process. And it could be deep learning, it could be even using SVMs or something like that. Okay, so that's the context. Okay, so now we are switching over to NLP. Okay, so I just wanted to, I think this is just again an aside about CNNs. I think last time and last two lectures, in fact, we spent some time on CNNs. I just wanted to show you one of the, this 5 years ago, the best paper in a top conference in this area for images and vision. It's called CVPR. It's a top conference for academics, and so as well as industrial researchers. So you can see these authors defined a new network architecture, layered architecture called densely connected convolutional networks. Okay, and their key innovation was that hey, why are we passing tensors from one layer to another? Which is what we do in CNNs. Why can't we? So let's say the first input layer is basically a input tensor. Why not we just pass it to the next CNN, but next con layer, but also to the con layer two rows below, or 2 layers next, or con layer 3 layers down and 4 layers down, and so on. So every tensor is being passed to not just the immediate next layer, but also the subsequent layers as well. Okay, and of course there now comes up, how do you deal with dimensions? These are cuboids. How do you deal with them? But more than that, with these dense connections, so every layer every tensor is being sent to not just the subsequent layer, but all the layers that come later. It seems like they have achieved some interesting improvements on the usual data sets. And in fact, you can see one of the data sets being referenced is CIFAR-10 object recognition benchmark. So this is just from 5 years ago. There are a lot of such innovations that people have tried out. Some are very good empirical patterns that we kind of look at them in courses, but some of them may be very specific to a domain. So I just wanted to point out an example like this. So let's actually come to NLP. So outline is in 3 steps. First, we will look at some basic introduction to NLP motivation. Next step is look at some simple models, okay, Naive-Bayes, latent digital allocation, and so on. Basically, these are going to be models with simple representations. So they're not really thinking about, hey, cat and dog are similar, but cat and an airplane is not similar. Okay? That similarity is not being captured at all. Okay, so we'll look at those simple models first, and then talk about, hey, they have these gaps, and so let's fill that gap via this notion of word embeddings. Okay, so again, embeddings are just, at the end of the day, for each word, give me a vector for that word, and I can work with that vector, and the vector hopefully captures similarities. Okay. Okay, so natural language is basically So natural language processing concerns with all aspects of natural languages, which are basically human languages. We of course cannot do the whole area of natural language processing justice in this such a short treatment, couple of lectures, but we'll sample a very narrow set of topics that have come up over the past decade, basically. And we will we'll sample a few ways to deal with text, and some of which we already are aware of. So text is basically, you just think of it as a sequence of symbols, right? So you can think of words themselves at the word level. Each word could be a symbol, or we already have characters which are symbols, right? So text is a sequence of symbols, and so you can think of that as like a time series, but it's some resemblance to time series. Now the naive way is to represent words or characters as one hot encoded vectors. Okay, so each word, if it's a symbol, you can think of it as a category value, right? So then you have maybe there are 50,000 words in dictionary, then the 50,000 category values, and so you can actually have a 50,000 dimensional one hot encoded vector where the coordinate for that word is 1 and everything else is 0, right? That's what one hot encoded vector means. So that's naive way. I mean, at least that's one initial approach, but it has its shortcomings, and we'll see some better methods today. Okay. So let's actually motivate ourselves with some examples first. Machine translation is a very popular example, a very popular application for being able to work with natural languages. Okay, so there's so many countries in the world, and many countries have different languages, and so being able to go from one natural language to another, for example, from given an English sentence to give a high quality Spanish translation of it automatically using machine learning is something that's been iterated upon, and actually there are commercial products these days freely available and so on. So all the advancement there, in general, it's called machine translation, has happened even before deep learning, but also with deep learning they have also improved leaps and bounds. Okay. Another example is more, I guess, challenging is query answering, so question answering, basically. So,
Professor.
Yeah.
So what kind of database would we need to train like a translator like that?
So we are actually going to train a translator in assignment 3. Okay. So for this, we actually just need a sentence translated sentence pair. So this is actually still supervised learning. So you do need somebody manually saying, hey, for this sentence, this is a translation. Okay. So as long as you have those sentence pairs, then we can, importing the data into Python or whatever, there are some quirks very similar to how we'll have to deal with images. But once we can import the data into Python, you can actually just, it's called sequence problem. And so next lecture, we'll be talking about RNNs and so on, which are the type of models that you will use for this. Okay. So in assignment 3, we'll do this actually. Okay. And you get to choose your language pair to do it. Yeah. Yeah. So all you need is supervised data, which is typically hard. Okay. If you pick a very unknown language, as in the sense that if there is no previous annotation already, then you'll have to spend money or whatever to kind of find sentence pairs and curate them so that you can actually use them for training. Yeah. And these models here today will not see. We'll not see this, but tomorrow, sorry, not tomorrow, but next lecture we'll see a model to do this. Yeah. Yeah, let's move to the next example, which is just query answering. Here, these are really hard problems, right? I'm talking about some aspirational, types of problems here. Some of them have some versions which are implemented by researchers and so on. So here's a document, and the query is like, what does the article say? I mean, what are some question about the text in the document? Okay, and an ML model or an AI system should be able to answer correctly to that query. Okay. Now again, this requires supervisory signal. Okay, so we are still in supervised learning land. So there has to be some existing corpus of documents and queries and answers, from which it will detect, hey, for certain types of documents and certain types of queries, I should pick up certain types of entities, maybe names, maybe places, maybe things like that, right? So that's query answering, and different versions maybe have applications, different settings. Speech to speech itself may need to go through not just may, but it typically goes through a natural language translation layer, which is that from speech signals, first of all, you want to kind of decipher what sentence it is in whichever language it is, then do machine translation, which we just discussed 2 slides ago. And then again, from that translated sentence, you go back to speech. Okay, so instead of, so this at least, breaks the problem into modular sets so that you can worry about speech to text, text to text, and then text to speech, instead of directly from speech to speech, which is also something you can do. You have one time series as input, one other time series as output. You could do, but that's that's more seems more challenging. If it's not modular. Okay. Here's a more another interesting application, which is visual question answering. So here the input is an image and not text, but the question and answer are text. Okay, so which is which you can see here, some questions asked from this image. Okay, so there are prototype demos which kind of can do this, but the success really depends on what's the corpus, what's this application, and so on. So all the, for example, Google Images, for example, is a product, or vendors like or social media platforms like Instagram and so on. So they do they do build these types of systems to be able to understand more about the images that they hold or serve or whatever, right? But in general, text itself is a hard problem. Forget about, in the previous slide, we were talking about images and then answering textual question answers there. But even working with text itself is hard, right? So, here are some example issues, right? So the sense of the word could be unclear just, based on the sentence. For example, I saw her duck. Could mean, seeing somebody's duck, or that person ducking under a table, for example, right? And similarly, just in English, and these are just examples for English, right? There are idioms which, could mean something completely different. So the fourth sentence here is completely different from what the previous 3 sentences talk about. And similarly, the reference to objects and their properties, is confusing in this example sentence. The ball did not fit in the box because it was too big or small. Depending on whether we use big or small, it could refer to ball or box. Okay, so this is one example of complexity. There's so many such, I would say, edge cases that they're no more edge cases. They're actually a good chunk of ambiguity and complexity introducing aspects of natural language. Okay, and that's why you can get to a like a 50-60% performance level kind of without too much work. But beyond that, there's so many such concerns that's it's not easy to address. Okay, so so the motivation for the previous few slides were just to get a sense of like what are the type of applications they're talking about, right? But some applications that I've skipped are some of the more natural ones that you might have seen, like sentiment analysis, understanding review scores, right? So Google may summarize, given thousands of reviews, what is the properties that are being discussed, or maybe TripAdvisor or Airbnb, I don't know, or analyzing social media, text, right? Twitter, or analyzing financial documents of firms to understand their outlook and whether they're doing well or not. So there are many other applications, and depends on the industry, that I've not touched, and they all may have to do something with text, right? So text is a great source of human-generated content, human-generated data. And it's unclear what's the best way to pass it to a machine learning model. And we'll see through some examples today. We have at least one candidate, which is vector representations of words, by which you can work with machine learning. Okay. So let's start with some simpler models. I'm just all relative, so simpler models, which what they do is basically to sidestep word-to-word relationships. So in the sense that they're not worried about word-word relationships. Like, hey, word cat and the word dog are kind of related to each other. They're both referring to animals, and they're both referring to similar types of animals. So that's kind of ignored. Okay. And some of the examples, and we'll probably not go through all of them given our time constraint. First one is a naive Bayes model. The second one is a Markov model. Third one is the latent digital allocation model for topic modeling. We will not look at conditional random fields, conditional random field based classification, but that's another model that's that people can use. And the last one is CNN based sentence classification. So what we'll do is it's not the purpose of this section is not to really introduce each of these models in a lot of detail. The purpose is just to kind of really focus on, hey, maybe they're not, they're good models for whatever they do, for example, classification and whatnot, but they kind of don't capture word semantic, not semantic, but let's say they don't capture word-word relationships. Okay. So let's start with the first model. Okay. So what is Naive's model? Let's maybe talk in terms of the typical example that everybody gives, which is spam classifier. So here the model is basically it's a probabilistic model. Okay. So which is the model is saying that the conditional probability of the features, let's say word 1 to word n, given the label, which is spam, is independent. Okay, so conditional probability of the words just boils down to the product of the probabilities of the words themselves. Okay, so it's like given spam, the joint probability of these words is the product of is the same as the product of the individual probabilities. Okay, so words occur independently of each other given the label. So given spam, word 1 has nothing to do with word 2 occurring or not. Similarly, given not spam, word 1 has nothing to do with word 2 occurring. Okay, so this is the assumption, and so under this assumption, how do you so what does the model do, right? So what we want to say is that, hey, given a bunch of words w1 to wn, let's say w1 to wn represent whether the word is present or not. Okay, so just a binary variable is it's basically one hot encoding, right? So it's a slightly different one hot encoding where it's like indicator of whether word is present or not. Okay, actually it's kind of equivalent to one hot encoding. So given whether word is present or not, you're saying what is the probability of spam, what is the probability of not spam. Okay, so this conditional probability is by base rule is the probability of spam times this probability of words given spam, which we assume to be conditionally independent, and that's why we're getting this product representation. Okay, so that's the model. So given any sequence, given any word 1 to n, presence or absence of them, you can say whether that input is a spam or not. Okay, and for that, what are the parameters? You need to find out, hey, what's the probability of spam? Okay, that's something you want to estimate from training data, and you also estimate from training data what's the probability of each word given spam, and probability of each word, for example, also given non-spam, and so on. Okay, so so the model is about just conditional probabilities of words given spam or not. Okay. Yeah, so here's a pictorial representation of what the assumption is. It's just the probability of words given spam. It's just the product of words given spam. So the way it's represented here is basically as if like each random variable. So wi and spam are random variables. So they are just denoted as nodes of on a graph. And then the nodes are connected to each other if, like for example, wi is connected to spam because wi, so wi is not independent of spam. Okay, so but w1 is not connected to w2. It's only w1 is connected to spam, and w2 is connected to spam. And so this is just a graph representation. Let's not worry too much about this graph representation. But it's just trying to capture this the equation that's shown in the bottom, okay, bottom left. This probability of words given one of the classes is just the independent probabilities of words given the class. Okay, so it just factorizes. Okay. So given this model, given this model spec, how do you compute the parameters of this model, right? So given data, what do? You just count. So let's say it's two classes, spam versus no spam, or spam versus ham. Then probability of each word. So in this slide, the W's became X's, but just think of X's as W's. So probability of X, a word being present, is Xi being true, given the label, whatever label it is, spam or non-spam, is just the number of times the word appeared and it was spam divided by the number of times it was spam. It's just the counting. Hey, how many times was this word when in the data where those emails corresponded to spam divided by the number of emails which are spam. Okay, so it's just a counting and normalizing going on here. And similarly, what is the probability of spam itself? Hey, if you have a data set of 1,000 examples, maybe 40 of them are spam, 400 of them are spam, then 400 divided by 1,000 is the probability of spam. Okay, so it's a very simple estimation of these two parameters that are needed to estimate spam or not. And then once you have these parameters, you just go back to this formula here. Probability of spam, probability of each word given a spam. And so given whether some words appeared or not, you can say something is spam or not. Right? So any confusion about this model? It's just a warm-up model. I don't want to confuse anybody, but if you have seen Naive-Bayes model, the crux of the idea is just this, right? This conditional independence. And the right-hand side, you can estimate from training data. Okay? What is the proportion of spams, and what is the probability of a word occurring if it is spam? If you can estimate those, then you can tag for any new collection of words, or basically a new email, you can say whether it's spam or not. Okay, so let's move to the second model, which is what is called a Markov model. So yeah, what is called a Markov model. Here in this illustration, we're just talking about a character level Markov model. So what is a Markov model? Markov model is a very simple idea that you want to compute. So it's a Markov model is basically a model which makes the Markovian assumption, which is just that if you have a collection of characters, let's say for example here you can see there's a collection of characters, right? Character C followed by character H followed by character A followed by character R followed by character A and so on. In Markov model, the objective of the model is to generate the next character given the previous characters. Okay, so what is the model's input output? Input is, hey, what are the current characters? Given those characters, tell me what the next character is going to be. Okay, so of course, for example, given LA, the next character could be N, and the next character could be anything else also, right? So there is some probability with which the next character could be N, some probability with which the next character could be some, some other character and so on, right? So what you do is build this model. So you first decide how much. So what is the input size? Okay, whether I'm going to look at look at 2 characters before, or maybe 3 characters before, and so on. Okay, so that is an order. So let's say you take 2, and then you say, hey, given these 2 previous characters or words, words in general, but in this slide it's characters. Given those 2 characters, what is how many times did those 2 characters precede the letter N divided by the number of times those characters appear? So here's a different example with the word hello. In hello, let's say I want to find the probability of character L given HE. We're just looking at our training data and saying, hey, how many times did HE and L appear divided by how many times did the HE appear? Okay, so that's the probability of seeing L given HE. Similarly, you'll compute probability of a probability of any other character given HE. So you will have, like, let's say 26 different numbers, right? Or whatever is the number of characters you want to have. And so you will have such a estimated number for all possible characters given all possible, previous characters that can appear of size 2. And once you have these numbers, then you can predict for any given pair of characters what's the next likely character, for example. Okay, so that's why it's called a language model, because it's just predicting the next character in sequence given the previous characters. Okay, and it's Markov because it's not looking at all the previous characters except for the last 2. Okay. So there's a question from Shubham. Is auto-completion of text an application of Markov model? Yes, that's a great application. So on cell phones, this is a good benchmark time series model. Okay, especially if your time series is not numeric. Okay, now the moment you have time series which is not numeric, you can just do this. Okay, so it's just looking at, hey, given the previous two values, what's the next, given previous two characters or previous two words, what's the next word that should appear? Okay, that's what this Markov model is doing. Okay, you can even do it for recommendations actually. Hey, given that this user picked up item 1 and item 2, what's the probability that they'll pick item 3? And then from training data, you can get those probabilities. Hey, in all the training data, item 3 appeared with item 1 and 2 divided by how many times item 1 and 2 themselves appear. Will give you a sense of how likely item 3 is. And then you can use that to recommend like the third item, the fourth item, and so on. Okay. So yeah. So you can actually generate new text by sampling here. And this itself already gives you a decent language generator. If you have played with any language generators online, and maybe next class we'll look at, or two lectures from now, we'll look at a couple of language models. But you can already generate text. Okay, so I mean, you can generate at the level of characters if you do a character level model. But if you do it at the level of words, you can actually generate words and potentially create a sentence. And it may not be that coherent, but it may be coherent. Depends on the corpus and how you've learned the parameters. Okay. Okay, so what I want to do next is talk briefly about a model called latent Dirichlet allocation. Okay, it has some different names, right? It has different phrases, different words in the name, but it's basically what is called a topic modeling approach. So what is the topic modeling problem? It's just that you have been given a collection of documents. So think of really, newspaper articles from, New York Times over the past year. And then you have not annotated the data. So you have documents, which is a collection of words. And in particular, in this modeling approach, we'll even ignore the order of the words. So it's just each document is just a bag of words, essentially. And what we'll do is do an unsupervised clustering of those documents, which essentially mean that each document we're gonna assign to that some sense of, hey, its topic is sports, or its topic is music, and so on. But these assignments of labels like topic is sports or music, we're not going to do it explicitly. Okay, and we'll see in a second how we do it. So that's the objective. So unsupervised kind of clustering of these documents. Okay, that's the objective of topic modeling. For that, we want to understand one distribution called Dirichlet distribution. And this figure is trying to show you what a Dirichlet distribution is. It's basically, it's a distribution over, it's a distribution, for example, here, so just like normal distribution or Bernoulli distribution, like Bernoulli is, think of Bernoulli distribution as parameterized by a bias of a coin, and Bernoulli distribution, to specify Bernoulli distribution, you just need one number, which is the bias of the coin, right? So for Dirichlet distribution, it's a distribution over vectors. Okay, it's a distribution over vectors, and so here you're seeing a 3-dimensional plot. So it's a distribution over 3-dimensional vectors. Okay, and the interesting thing is that those 3-dimensional vectors, they're always positive and they sum to 1. Okay, so it's just a distribution over vectors, but those vectors are kind of not arbitrary 3-dimensional vectors. They can, are arbitrary 3-dimensional vectors in this illustration here. They can only be those vectors which have, which are all positive coordinate wise, and they can only sum up to 1. Okay, and so those vectors are represented by this triangle here. Okay, that's the, those vectors can only be on this triangle on a plane in 3 dimensions. And this distribution showing, hey, if you see a bump here, it just means that that vector is more likely compared to vectors on the side, and so on. Okay, it's just a distribution of vectors which sum up to 1, and they're positive. Okay, so why do we need that distribution? Is we just need that for specifying the model, as we define the model. Okay, once we define the model, we can estimate the model parameters. So let's understand what the model is first, and then we can talk about estimation and stuff later. Okay, so given documents, what we want to say is, hey, document, we want to say that there are some topics which are like politics, religion, sports, music, and so on. And we want to kind of say, hey, this document probably is, maybe 30% politics, 20% religion, 20% sports, and so on. So that's the kind of output you want to give. So given a document, you can say, hey, this is 60% sports, 40% music. Okay. But where do you get this list of words which kind of correspond to those topics, right? So we'll talk about that in a second. So which is that, yeah, so bottom is just exactly showing what I said. Given a document, you want to say, hey, whether 50% finance, 49%, sports 1%, and so on. So how do we get these pink boxes, which are topics themselves? Okay. So the way we get it is actually this pink boxes are actually all the words. Okay, all words in the so each pink box has all the words in the vocabulary. Okay, so let's say the vocabulary has 50,000 words, then each pink box has all 50,000 words. What changes from one pink box to another? So is that for the pink box with the top, which we call as a topic politics, the words corresponding to the political topics, those words will have higher probability. Okay, so this pink box is not just the words, it's the words and the probability of these words. Okay, so the probability of the word president is going to be high in this pink box, whereas the probability of president is going to be low in this sport box. Okay, or sport topic. Okay, so topics are nothing but, think of them as Python dictionaries if you want. It's just a key, which are the words themselves, and some probabilities associated with each word. The probabilities are going to be higher for the topic for the topic related words, and probability is going to be lower for the non-topic related words. Okay, so that's what these are. It's not that we'll predefine them. These are actually learned from the document. So it's an unsupervised problem. So given some collection of documents, we will learn such topics. And then for any new document, we'll be able to say, hey, it's 50% of one topic versus 49% of the other topic, and so on. Okay. So what is the model? It's again a probabilistic model. So the one way to kind of discuss the model is to say, hey, how would is to say it in the reverse way, which is that given topics, can we in the reverse way, which is just that given that model, can I generate a new document? Okay, can I generate some document, or can I generate a document? New document, a document is all the same thing. It's a generative model. Okay, so if people are familiar with discriminative and generative models. Generative models are probabilistic models where you can either say, hey, given some random variable, what's the probability of another random variable? Or you can say, hey, let's start with one random variable, then realize another random variable. This is how the data set gets generated. Okay, so that's the but that's the perspective that we'll take. Okay, so how do we this is all under the model. We're going to now talk about how to generate a document. Okay, so first what we do is so there's going to be a Dirichlet distribution. Okay, again, I said Dirichlet distribution over vectors such that the vectors sum up to 1. The coordinates of the vector are such that they sum up to 1 and they're positive. Okay, so let's for simplicity assume that the number of topics is 3. Okay, so Dirichlet distribution will have 3 parameters, which are here represented as alpha, from which we're going to get a vector which is going to be 3-dimensional. Okay, so 3-dimensional vector, numbers are such that they sum up to 1 and the numbers are positive. Now it should immediately ring a bell that this, whatever the Dirichlet distribution generates, is actually a probability mass function. It's already a probability mass function, right? Probability mass function is just, it's a distribution. Okay, so this distribution theta, you can consider it as a distribution over topics. Okay, how many topics? 3 topics. For us, let's say capital T is 3. Okay, so theta is a distribution over topics, and we already said once you sample a theta, let's say theta comes out to be 50, 49, 1. Okay, so then those are the 3 numbers. So those are the 50 by 100, 49 by 100, 1 by 100. Okay, then those are the 3 topic proportions. Okay, next what we'll do is generate words. Okay, so first we already decide how many words the document will have. Let's say capital N number of words. Then what we'll do is generate the document in 2 phases, 2 steps. First step, which is like a step number 2 in the slide, is that for each word, each word that we would like to generate, we have word index 1 to n. For each word, first we'll decide what topic it should belong to. Okay, we already have theta, so we already got theta. So for each location, we'll say, hey, let's generate a since theta is a probability mass function, I can generate a sample from it. Okay, it'll say, hey, either topic 1 or topic 2 or topic 3. So for first word, I'll say, hey, generate a sample. It'll say, hey, topic 1. Okay, that's good. So first word will be topic 1. Next, I'll move to next location, which is, I'm going to figure out word 2, for which first I'll try to determine what is the topic for word 2. Again, I'll sample from theta. It'll say, hey, topic 1, 2, or 3. Maybe it's topic 3, and so on. Okay, so we'll first decide the topics of the words. Okay, that we haven't figured out the words themselves yet, but we know at each location what topic it should be. And then in the second step, we're going to actually draw a word from that topic distribution. So remember, each topic, as I said, is just a dictionary which has the words and the probabilities of those words. Okay, so let's say the first word is sports. Okay, or in this, first word is related to weather. Then we'll go back to the weather dictionary, and the weather will say, hey, this is the probability with which each word can occur. And so if we sample from that dictionary, or basically that distribution of 50,000 words, then one of the words, most likely a word related to weather, will be the one which will be sampled, and so that will be the first word, and so on. Okay, so that's the generative procedure of generating a document. Of course, it's not going to be coherent. Certainly, it's not going to be actually. It's just a mumbo jumbo of words where some words are kind of drawn from one topic, some words are drawn from some other topic, and so on. Okay, so that's the generative procedure. And if you have this generative procedure, then now that we have this, to have this generative procedure, you need to learn the parameters. Okay, alphas and betas. Okay, so alphas are the parameters for which to get the topic distribution from, and betas are the topic specific probability mass functions. So per topic, what is the probability of each word, right? So those are the parameters of this model. Given a corpus, we can learn that. Okay, so for example, in the bottom of this slide, you can see that given documents, we're actually figuring out, hey, politics topic will have a distribution of words like this. Okay, president will be 0.0095, Obama will be 0.0090, and so on. And similarly, religion topic will have some distribution over words, and some sports will have some other distribution over words. Okay, so given documents, this is what you learn, and you'll also learn that this distribution parameters. Once you know that, then any new document, you can actually say, hey, it is 50% weather, 49% sports, and 1% music. Okay. Any questions about this? How does LDA compare to latent semantic analysis? As a question by Shubham. So latent semantic analysis is actually another name for PCA. Okay, so PCA, as you know, is a dimensional reduction technique. Again, unsupervised learning technique. So it's more about vectors and projecting vectors to lower dimensions. Okay, so that's what latent semantic analysis is, LSA. LDA, on the other hand, is a particular technique in topic modeling. Okay, there are other techniques, but LDA is a specific example of trying to do an unsupervised clustering of documents. Okay, it's not exactly clustering, right? So each document, if I say, hey, it's topic 1 is 30%, topic 2 is 20%, topic 3 is 50%, whatever it is, then you kind of, in an unsupervised way, learned that, hey, some documents are of this, has a majority topic this, some other documents have majority topic this, and so on. Okay, so it's like a clustering approach. Okay, so they are not very related. And also there's another acronym called linear discriminant analysis. Okay, linear discriminant analysis is something that you might have seen in 575 or 572. So that is related to classification. Okay, typically binary classification. So there it's a linear part corresponds to it being a linear model, and linear discriminant analysis has some assumptions about the distribution of the features given each class. Okay, so that's a different again, not to confuse any of you, that's a different model. Okay, so here so just think of LDA as a technique within the set of topic modeling techniques. Okay, it's still quite popular. It was introduced in 2003, if I recall, and you can do topic modeling, for example, on tweets. Okay, so in tweets, you have a collection of tweets. You wouldn't necessarily know what each tweet is about. I mean, it may take an effort to annotate tweets if you want to use some annotation services. Instead, you can actually try to find topics in an unsupervised way like this. Yeah, so let me not spend, I mean, this slide is exactly saying what I already mentioned. Each word, first you assign a topic, and then you sample a word from that topic distribution to get the word itself. Okay. I'll skip this. This is just the same thing represented in a diagram, but the explanation, the generative procedure should make sense from 2 slides ago. So it's the same idea. So let me skip these 2 slides for now. Okay, so far, so we've seen already 3 models. Okay, and each of these models, first model, naive Bayes, it was not really, the words were just random variables, whether the presence or absence of a word, but the word itself being cat or a dog or an airplane didn't matter. Okay, so there was no word-word relationship. Of course, the presence or absence of a cat may influence, of course, whether it's a spam or not spam, but there was no representation of the word. It was just a one-hot representation, the word present or not present. Similarly, in a Markov model, again, it was not, there was no, like the meaning of the word was not kind of explicitly taken into account. Okay, so the word cat and dog, again, same thing. They were just abstract symbols. Okay, there is some frequency with which they co-occur, and maybe some frequency with, the next word can occur given the previous words. But there's no, again, like word-word relationships are not captured. And same thing with topic modeling, right? So although each topic is about topical words, so some words are higher probability and some words are lesser probability in each topic distribution, but the words themselves, whether the word, let's say baseball, and the word soccer, they're again abstract symbols. Okay, so they're not, you don't look at their context in which they occur, for example. So let's look at one more model, which is a CNN-based sentence classification. And this is in a sense a model which does require, which can work with both one-hot encoded word representations as well as the word representations that we're going to discuss later, which are basically word embeddings. Okay, so this is like a teaser. So this is an example where you can use word embeddings, but you can also use one-hot encoded representations of words. Okay, so I'll talk about, I've been using one-hot encoded representation of words. We'll see an example where explicitly will be very clear what is the one-hot encoding representation. So let's say you have an input is a sequence of words, basically a sentence. The output is a class label. Okay, some, label 1 versus label 2. So the input is a variable length, right? Sentences need not be all of same length, right? So some sentences have 5 words, some sentences have 10 words. And given the sentence of variable length, you want to say, hey, it is class 1 or class 2. So you can imagine sentiment classification or anything else, those types of things fall in this this category. There are a couple of things you can do. You can ignore the order of the words. Certainly, you can drop that, and you can ignore semantic information, which is like the word themselves. You can just think of them as a fixed length bag of words. So let's say the vocabulary size is 50,000, then you'll have 50,000 dimensional vector where locations where the words are present will be ones, and where there's not present, zeros. Given that 50,000 dimensional vector, one-hot encoded vector, you predict one of these fixed classes, right? So now we've changed the problem. You've ignored sequence, ignored word details themselves. Okay. Here's another example where you can have if you had word vectors, and this is where I'm saying we're jumping ahead, which is that if you had some representations for words, okay. For example, if the word is really one-hot encoded, then this weighted average is exactly going to be very similar to the bag of words representation. So the weights will be, maybe some words are more frequent, maybe higher weight, and so on. Okay. Again, you're losing word ordering. So sentence, the order in which the words appear in sentence. And then you retain some semantic information because you have, at least if you have some interesting word vectors, representation of words instead of the one-hot encoded vector, then there's some semantic information, and you can still maybe go from a fixed size input to an output. Okay, so let's actually look at the CNN version. So if you remember CNNs from last class, it's just a way to convolve. Okay, so let's only think of a depth 1 input. So which is that there's no this input is, if you think of an image, just think of image as having no depth. So there's no RGB channel, it's a grayscale image. Then we know how CNNs work. For example, the con layer, it'll have is defined by a bunch of filters. And so each filter just slides on the input and produces an output, right? Slides from top left to top right, and then one cell below. It depends on the stride and those choices, but top left to top right, and all over the image, and then you get an output vector or a matrix here. And so we'll use the same idea to define a CNN-based sentence classifier. Okay. So why CNNs? As we said, location invariance in images for certainly, because whether the image of cat appears wherever it appears, it doesn't matter. It's still you want to classify as a cat. And compositionality, right? So lower level features feed to higher level classes. So maybe cat has those pointy ears and whiskers and so on. So if you detect those lower level features, then eventually it boils down to a high level pattern, and maybe you'll say it's a class is cat. Right? So what we do is now, but CNNs only work with images. Even if you have a grayscale image, you have like a 2D representation. So we are somehow going to make a sentence into a matrix. Okay, that's what we'll do. And how do we do that? So let's say a sentence has 7 words. Actually, 2, 3. Yeah, let's say a sentence has 7 words. Then what we'll do is represent each word as a row in a matrix. Okay, so that representation of the word of a row in a matrix, it could be a one-hot encoded representation of the word, which could be really long, or it could be some other representation of the word. And we'll see that other representation later on in this class. Okay, so let's focus on the left side of in the center part of the figure where I'm using my cursor. So I like this movie very much. Each word or each symbol or each token basically is represented by a 5-dimensional vector. Okay, so I is represented by a 5-dimensional vector, like is represented by a 5-dimensional vector, and so on. Now, either you'll know these vectors beforehand, which is what we'll do with Word2Vec or vector word embeddings. Okay, or you have a one-hot encoded representation of these vectors, which could be really long. It need not be 5 here. So somehow you start with this matrix. Okay, and then you can do convolution to get to your sentence classification. So what is this figure trying to show? It's trying to show 3 sets of convolution operations. Okay, so you can see what are these color blocks in the center. Okay, so these are actually 6 filters. Okay, 6 filters. So this top brown one is actually a filter, and the center red one is also a filter, dark green one is a filter, light green one is a filter, and so on. Okay, so these filters, so again, filters are also matrices, just like in the previous figure, right? The filter is also matrices, and input is also matrix here. Similarly, here the filter is also matrix, but the filter width is the same as the input width. Okay, so the filter doesn't have scope to go left to right. It can only go, first of all, if you think of this brown filter overlapping with this input, it'll occupy, let's say the first 4 rows, and that's it. There is no sliding. There's no sliding to left and right. Okay, it just occupies the first 4 rows, produces 1 number, and then it can only slide 1 step down, and it produces a 2nd number, and 1 step down produces a 3rd number and 4th number. Okay, like if let's take the other extreme, which is this yellow filter at the bottom. Okay, so how does this yellow filter work on the input? This filter has 2 rows. So first you multiply. First you put the 2-row filter on the first 2 rows of the input, do element-wise multiplication, sum it up, produce the first yellow number here that you can see at the bottom. Then that yellow filter, you slide 1 step down. Okay, so you can, so 1 step down. So like and this rows, again, you produce a 2nd number, and similarly this and movie rows, and you produce a 3rd number, and so on. Okay, so actually it's cut out, but it should have 1, 2, 3, 4, 5, 6 outputs. Okay, very similar to this previous one. So that's how the filter operations. Filter is not going left to right, it's actually going top to bottom. Okay, because left to right there's no scope, because the filter width is the same as input width. Okay, once you have that, there's a pooling operation going on, which is just averaging of numbers. Okay, so it's just taking the average or max of these numbers that's being produced at the next layer here. So after pooling, there's only one number per filter's output. Okay, one number for filter's output, and then those one number each are actually aggregated together, and then from that fully connected layer, you know how to do multiply with a matrix and get add a bias to get to a lower dimensional vector, which is a score vector. Okay, so that's an example from a 2015 paper or 2016 paper, which appeared in a top conference in natural language processing. Okay, so any questions about this architecture? Okay, so this is just to, so the purpose of this example architecture again was to show you that CNN's conv layers can also be used for sentences, only because we were able to represent the sentence using a matrix. And the moment you have matrix, which is a very, it's the simplest tensor, then you can think of convolving operations again on a matrix, right? Just like what we could have done with a grayscale image. That's exactly what we're doing here, except there were specific choices being made, which is the filter width is the same as input width, kind of, did not, it made it like a sliding operation was just sliding up and down, basically. So other than that, it's a specific architecture that was proposed in this paper that you can see in the bottom left reference. And it seemed to perform really well. Okay, and I mean, this is just an example of how if you learn one model really well, you can kind of see if you can use the same architecture or similar ideas, layers in other seemingly very different domains. Okay? But you can see that there's one important thing that we kind of glided over, which is that, hey, how do I get this 5-dimensional vector representation for the word I, 5-dimensional vector representation for the word like, and so on. Okay, and that's the context for the next part. But let's take a 10-minute break and resume at 5:25. Okay. And if you have questions, yeah, what are the two labels here? So in this sentence classification, it was a generic sentence classification. You can think of that as you can even think of this as spam classification if you want, right? So given a sentence, you can just say, hey, positive sentiment versus negative sentiment, or spam versus not spam, and so on. Okay. So the application itself is just, it doesn't even have the two classes. It can be more than two classes, but it just wanted to show you that, hey, if you want to classify sentences, whichever application it is, this is one way to do it. Okay, with decent results as shown in this paper. Okay, but it will need some vector representation of words. And one candidate of that is what we'll see in the next section of this slide deck. Okay, so let's take a break till 5:25 and resume. Yeah. Okay, let's resume. So we're going to switch over to an approach which tries to capture word-word relationships. Okay, and that's the idea of word embeddings. So basically, what's the objective, right? So the objective is to have similar words be represented similarly. Okay, so semantically similar words be represented similarly in a vector space. Okay, so words will need to have vector representation. So for each word, for example, you have a 5-dimensional vector representation or a 300-dimensional vector representation. But those vectors should be such that similar words, semantically similar words, should actually have similar vectors. Okay, so what does semantic similarity mean? Basically, words that appear in the same context share semantic meaning. Okay, so semantically similar words appear in similar contexts. So the word cat and dog appear in similar sentences. So perhaps their vector representation should be similar to each other. Okay, there are two approaches actually to capture this semantic similarity. One is count based. So you can just look at counts of how many similar contexts have a pair of words appeared in, or it can be prediction based. Okay, so in fact our approach will be prediction based. It's not really a deep learning, it's some neural network involved, but it's not really deep learning, but it's going to be a prediction-based approach to get these vector representations. So see, our objective here is to just get from a word to a vector representation of it. Okay, so that's it. And so you can either use counts, just, hey, pick 2 words, cat and dog, and look at all the contexts in which they appear, and all the contexts in which they appear, how many common contexts there are, and that's some sort of a sense of, hey, how similar are these words semantically. Okay, so that's count based. And then once you have these counts matrix, basically for every pair of words, you can do some dimensional reduction or some factorization, for example, PCA, to get word representations. Okay, so that's the count based approach, but we'll be really focusing on only prediction based approach, where we want to somehow learn learn these word representations while taking into account that, while building an auxiliary prediction task where if words appear in similar contexts, then hopefully they will eventually end up having similar representations. So we'll really be talking about this for the majority of the session today. Okay, so as I said, a word embedding is nothing but, you can think of that as a linear transformation or this matrix W, which, a word is an input, so a string is an input and produces a vector as an output. Okay, an n-dimensional vector. Typically n, you can think of 300 or 5 or whatever. So in the implementations that you can use, for example, Google produced these embeddings some time ago, and they use for example 300 as a choice for the dimensionality of the vector. Okay, so for example, university will have some vector and class will have some vector, and hopefully the vectors probably are closer to each other than university and maybe a country. Okay. So how do we learn this vector representation of words? Okay, which is literally encapsulated by this linear transformation W or this function W, right? So the idea is to initialize W. So initialize this W, this function, such that it's producing random vectors for each word, and then hopefully this W is parameterized by things that we can change, in fact, parameters that we can change, so that, eventually, keep changing these parameters such that eventually the vectors for each word are actually meaningful. Okay, are representatives, have semantic representation captured in them. Okay, and so how do we change these parameters? We have to do some gradient descent, and so there's going to be an appropriate task that we'll define. Any questions here? At least the high level, what we're trying to do, we just want to get from words to some vectors, and hopefully those words which appear in similar semantic contexts, similar contexts, we will call them semantically similar, and hopefully their vectors are similar. Okay.
So this way we are kind of saying, let's just somehow get some sort of vector representation for a word. So is this,
yes,
is this how deep learning is extended to anything? Let's just get a vector representation of something and then apply an appropriate methodology.
Yes, okay. not just words. Yeah, it can be for, even think of categorical variables that you have. Yeah, just get a vector representation for each category value, and then you're good to go. Yeah. So here we're going to get vector representation of words. And once we have that, then we can use it elsewhere. But sometimes you don't even care about using it elsewhere. You may be getting the vector representations as part of your original prediction problem or whatever it is. Yeah. But here, for today, we'll kind of restrict our scope to words in natural language, and really, create a kind of a useless prediction task, because our goal is really to focus on those vector representations. But sometimes your goal may not be to produce vector representations themselves, but also do well in the prediction task also. Okay. Yeah. So you're correct. So it's not just for words; it can be for any other, non-numeric object. You can get vector representations. Yeah. Okay. So it's a good question. Okay, so what we're going to do is kind of give an intuition for designing a task. Okay, so we said we're going to do a prediction approach to get these vector representations. So what prediction approach? So for that, we need to kind of say, hey, let's say we pick a classification approach. Okay, let's say we want to define a classification problem. because we're defining classification problem from completely out of thin air, because we want to get vector representations, but there are so many different classification problems we could potentially say. Let's take one candidate here, which is that we want to train let's say model, a neural network, to classify whether an input sequence of 5 words, 5 is some random choice. I'm just giving an illustrative illustration or an example classification problem. Okay, it's completely auxiliary, not kind of related to what we eventually want to do. We just want good vector representations. Okay, so the classification problem is, hey, input is a sequence of 5 words, and if it's a good sequence, as in like it is actually a naturally occurring sequence, then you say, hey, it's a good sequence. If it's some jumbled up words, then you say it's a bad sequence. Okay, so here's an example at the bottom of the slide, which is saying, hey, operates the largest medical school. It seems like a valid sequence. So the label for this sequence of words is valid, or 1. And then if you randomly jumble up one of the words, let's say you flip, instead of largest, put some other random word consistently. Okay, operates the consistently medical school. That's probably and then since you randomly jumbled it up, it most likely is not a valid sequence, and so you annotate a label 0. Okay, so now you have training data, so where a valid sequence has a label 1 and invalid sequence has label 0. Okay, and so this, now you have a classification problem. Okay, and while solving this classification problem, we will somehow learn that W, that either you can think of linear transformation, or basically we'll learn the vector representation of words. Okay, so if you so this is just for illustration purposes. We are actually going to go into the details of Word2Vec maybe next lecture. So today I just don't want to talk about Word2Vec implementation details, or that example right now. So we'll look at this illustrative example. So you start with, let's say, as I said, your W initially, this W box here is given a word. As I said, it produces some vector. Okay, ideally that vector should be a good vector representation for that word. But let's say it starts with some random vector representation. But it has tunable parameters. Okay, this W box has tunable parameters. So what you do is pass each of the word through W. Okay, and you get vectors. Maybe concatenate them one below the other, and then use a typical classifier like an SVM, or even a feed-forward network or loss aggregation classifier to produce whether it's valid or not. Okay, so now you have a full, like a computational graph essentially. And now you can say, hey, I want to minimize the loss. But while minimizing loss, you also change the weights or the parameters of this W box. Okay. So that's the way to, and the hope is that if you try to classify well, in order to do classification correctly, the parameters of W and C should be good. Okay, so it just means that, of course, you need to discriminate between valid sequence of 5 words versus invalid sequence of 5 words. But while doing so, the parameters of W have changed such that now W will produce better representations of the input words. Okay. The task itself is kind of not interesting. There could be other tasks that you can define, but this task is an example way to say, hey, here's an example classification task through which I can get an improved W, or improved representation of the words. Okay. So let's just kind of intuit why that's why this could work. Okay, so you can imagine if there's an invalid sequence like operates the consistently medical school, then one part of that input vector will be kind of different, right? So compared to words which are in sequence, words which are in sequence will have certain will give certain input vector here, and words which are not in sequence will give a different input vector here, and you're trying to discriminate between them. So and while doing so, you can adjust the weights of this W matrix, this W box, so that you can get better and better representations of words, such that when they are in sequence, they are very different from when they're not in sequence. And hopefully, you get vector representation for each individual word, which has some semantic similarity to related words. Okay, so in the sense that, if the words are semantically similar, they have similar representations. Okay. It seems like an indirect effect, but that's what we're going for here. Okay. I want to, I want to spend time on what is the precise prediction problem and really reason about why we would get good representation for words, but I want to do that with the help of a specific implementation developed by researchers at Google called Word2Vec. But let's sidestep that for a second and say, some procedure like this, some classification problem and training on it got us some representation of, so got us some W, okay, some trained W. And let's now think about what all we can do with it. Okay, and also give some examples of what all researchers did with it in when they trained such Ws. Okay, so 2 examples of such implementations of Word2Vec and Glow. Those are 2 names, and these are some of the oldest ones in the past decade. I mean, there have been many approaches like this, even before them as well as after them. So let's say you have some W. So what is W? So every word, you should just get a vector, right? It's basically a dictionary. Or you can think of it as a function or a linear transformation. It's just a collection of vectors. So if you have a W, what can you do? You can do the same thing that you did with images, right? So with images also, you had image embeddings, and you could embed them into 2 dimensions and get a sense of, hey, similar images. Let's say images of outdoor landscapes is very similar to images of is all clustered together, versus images of airplanes, versus images of houses, versus images of other things like automobiles, right? So similarly, you can use TSNE, which is just a nonlinear dimensional reduction technique, very similar to PCA. Okay, PCA is linear, TSNE and some other options are nonlinear. So you can use them to kind of visualize them. And here's a plot which seems very, can't read anything, but if you zoom in, yeah, so if you zoom in, you should be able to see, like, for example, here are some names of countries, and here are some months and days, and here are numbers on the left side, and other words. Okay, so this is just a way to kind of get a sense of whether your words are being represented with similar vectors in higher dimensions. Okay, so in 2 dimensions, if they happen to be close to each other, maybe they are close to each other in the higher dimensions. Okay, I just picked up this image from one of the better representations that that was created back 10 years ago. But it was just an example to kind of zoom in and see, hey, are semantically words which appear in similar contexts, are they kind of close in these 2 dimensions? Okay, so I'm not telling you which embedding, which W and which data set was used and all that, but you can look at this reference if you want. But this is one way to kind of understand, hey, do you have a good embedding or not? Okay, not just for words, but maybe even for any other categorical variable that you have, in case you get embeddings for them. Yeah, I think I already showed you numbers and months. So let me, yeah, and here's, I guess, a zoomed in version of that same plot from earlier. So these are the numbers and months, and so they happen to be close to each other, which kind of gives you some confidence that maybe in higher dimensions they have similar vector representations. Okay, because this projection techniques like TSNE, they try to preserve distances between higher dimensional vectors. Okay, so you can do a few other things, and this was something that folks did on some of the embeddings that they trained, and here's a reference at the bottom left. So what they did is looked at the closest words in the embedding to any given word. So to a given word, to a specific bunch of given words. So here you can see on the left is a particular word, France, and they're just looking at, hey, what are the words that are closest to this word in basically 10 nearest neighbors, okay, of this word. So you can see names of countries for when nearest to the word, the embedding for France. Similarly, embedding for Xbox has all sorts of games related strings or acronyms or even words. Similarly, colors, similarly, verbs, and so on. Okay, so that kind of is again another, very similar to debugging of CNNs. It's like debugging of a pre-trained word embedding. So word embedding, a word representation. You kind of want to understand, hey, is this a good representation or not? Right. So let's come back to intuition, right? So we saw that example classification task earlier, and the question is, so it's not the question about the classification, but the question is about, is it natural for words with similar meanings to have similar vectors? Okay, because we saw that here. And here's an example to kind of justify that, which is that, hey, if you change the largest to, let's say, biggest, these are very valid sentences or phrases. And so if W maps biggest and largest close, then the classifier should be able to work, right? So it's just trying to say that, hey, why are we seeing these are the nearest neighbors? Is because if in a whichever context or whatever 5-word sequence or whatever, France appeared, most likely in similar word sequence, these other words also would appear. Okay, and so even if you flip from France to, let's say, Austria, the word is still a valid sequence. Sorry, the 5-word sequence is still a valid sequence, and so that's why those two. In the sense, even if you flip from France to, let's say, Austria or largest to biggest, the classifier should still be able to classify correctly. And so that's why they happen to get similar vectors. Okay. So, but we are not limited to synonyms. Okay, so here we had not synonyms, but also, like, for example, the same type, country names, and so on. You could even have colors, right? So blue versus red, they're not synonyms of each other. Certainly they're, they fall into the same category, colors, but they're not synonyms. But still they may get similar vector representations. Okay? And they probably have in the previous couple of slides. Yeah, so yeah, so I just wanted to give some attempt at intuition of why why would you have these properties. Like, the focus really is on, let's say you had a word representation that was trained using some auxiliary classification task. Then, as I said, we could look at projections, we could look at nearest neighbors and make a sense of, hey, why would these make sense, right? Yeah, and that they're not limited to synonyms and so on. So here's a couple of a couple of other properties. So before that, let me just mention how much data that you need. You don't actually need, for example, for the inside wall is blue and the inside wall is red, you don't actually need both those sentences to be there in your training data, okay, to say that, hey, blue is similar, so blue is semantically related to red. Okay, so it's just that you don't need to see all combinations of words to get a sense of to get good embeddings. Okay, so the whole point is that you see some context where red appears, some context where blue appears, and there is some relationship. So it's not exact context that they appear in, exactly same context that they appear in, but the contexts are similar. Okay, and in that sense, you will be able to get similar embeddings for blue and red. Okay, so you don't need to see all combinations of all words to figure out that these words have to appear with these previous words or whatever context, and these words appear in this context. You don't need to do all of them. Okay, so they're similar to us, right? We don't see all words in all contexts, all sentences, but we are still able to figure out what word is appropriate in what sentence, right? Where is it valid and where is invalid? So let's actually look at some more examples. Like we saw projection, we saw neighbors, and here's another interesting property that comes out of some embedding, which is linked here in this paper. So they are saying, so the paper says that you're able to do some simple vector operations on these embeddings that you're obtaining. Okay, so in particular, whatever embedding they were analyzing. Okay, so here they're seeing the directionality of the vector when you subtract the vector for man from the vector for woman, you get a vector, a resultant vector which has some directionality. The directionality is the direction, or the vector even magnitude perhaps, is similar to the vector that you would get if you subtract the vector uncle from the vector aunt. Okay, they're just trying to look at some more effects of whether some other properties that they observe from such embeddings, so from such word representations. So like queen minus king has the same directionality as, let's say, woman minus man. Okay, and similarly here are many more examples like that. So you can, for a pair of words, you can subtract, subtract and add another word, subtract their difference, basically subtract those two and add another word, and you may get a word which is, which is the right analogy. For example, France minus Paris plus Rome looks like it'll give Italy, the vector which is closest to the vector for Italy. Okay, close enough to vector for Italy. Okay, so that's, that way you can get these relationships. France minus Paris is plus Rome will give Italy, plus Tokyo would give you Japan, plus Tallahassee would give you Florida, and so on. Okay, so these are some properties that folks have studied. Okay, these are very similar to studying pre-trained models that we talked about in the last lecture. Okay, so that was some example kind of ways to understand if you have these embeddings or not. But let's say you have these embeddings, what do you do with them, right? So embeddings are basically representing this unstructured data, these words, okay? And the interesting thing is they do capture these some amount of semantic meaning, right? The vectors getting embedded in certain ways. And we have already seen image embedding, so you can imagine these representations can also be used in similar ways that we've used image embeddings for. Okay, so let's look at some specific examples in natural language. Okay, just like for images, where we used transfer learning, say we said pre-trained model, or basically this in a feature extraction phase, at least feature extraction approach, at least you just get embeddings for you have the pre-trained model from which you can pass new images and get new embeddings. The model is a way to use to transfer. Here we don't need a model because they're only fixed number of words, right? So it's not like you, just like in images, you have a lot of new images. So you have to have, instead of just remembering embeddings for images, you're actually remembering the pre-trained network. Here we only have fixed number of words, so we don't need to, so here we just have to remember the embeddings of words themselves, because it's not like you create a new word and then we want to get its embedding, right? I mean, it can happen, but it's pretty rare. So what can we do with embeddings? So you can do the following, right? So you learn the word space or the word embeddings in a particular classification task, let's say classification task A, and then you can actually use the same word embeddings in another task G, okay, for example. Yeah, so some model G can use the same word representations to accomplish task B. Okay, so this basically, about a decade ago, 9 years ago, this is a phrase. So this is a quote which says that the use of word representations has become a key secret sauce for success in NLP systems. And all the examples that we saw at the beginning of this lecture, like even including, by the way, Google search or Bing search or any of these search engines, and other language, NLP related applications, have had impact from word representations like this. Okay, so named entity recognition, like recognizing words, events, places, names, parts of speech tagging, parsing, labeling, of different types. They all have been benefited from these word representations that can be learned on different corpora. Okay, and it's not just that the word embeddings can be used for other related tasks. You can actually do many other types of embedding. So we'll see, for example, you can actually map two different types of data into the same vector space. Okay, so you can embed English words into some vector space, and you can embed, for example, let's say Mandarin words into the same vector space. Okay, so you can, for example, this can help, this can give you actually a rudimentary translation, because something like this, right? So you can train these representations for word and English and Mandarin at the same time, where while training, you may know that some English words do have their, so while training, you may not know maybe translations for each word, but maybe translations to some pairs of words. Then you can impose that constraint in the loss, saying that, hey, whatever you do, when you get the embedding for one of the English words and one of the Mandarin words, at least for the ones that vectors should be close to each other. Okay, like this word university and the word, the Chinese word for university. So hopefully you want to impose that they should have similar vector representations. Okay, so if you do that, then it may turn out as a byproduct that for example, words that you did not know were similar to each other, or are semantically similar to each other, you would get that they are kind of neighbors to, you will learn through this embedding process, this joint embedding process, that they will be close to each other. Okay, so you can now start, you can get translations for words that you might not have known before. Okay, so I guess here's a pictorial representation. Again, they are represented in some higher dimensional space, projecting them into 2 dimensions. And here in green boxes are, I guess, the Mandarin words, and the yellow ones are English. And then they're both represented in the same higher dimensional space. And so if you project down, you can actually see some words that you did not know. There may be translations. You can find out nearest neighbors which are in the other language. Okay, so this way you can actually get word translations easily, if you did not have those translations before. Not just word, it's not just like 2 data sources getting embedded into the same space. You can actually share that embedding space across other data sources. Okay, so you can actually map, for example, images and words in the same space. Okay, so for example, you can map the image of an object near the object's word vector. And so, for example, you can map the image as the vector representation for dog. Like think of, let's say, the vector representation for dog should be close to the word representation for the dog. Okay, so you can say, hey, so let's say you have a convolutional neural network, and from images you're getting a representation for the image. Okay, and you're actually also getting a representation of the word. So you can impose, for some images you may have the labels, and you'll say, hey, for these images I want the image representation to be close to the word representation. So what does it do? For some new images for which you don't know the corresponding, let's say, word which should be related to it. Now, if you pass through, if you get the word representation and the image representation, then you can know from the nearest neighbors what the images related words are. Okay, so that's one example of learning related words to images through this shared embedding idea. So actually, there's an image here. For example, so let's say we embedded these words: auto, horse, dog. The word representations as well as the images. So images are represented by these plus signs, or these triangles or these squares, and let's say the word representations are by these dots. Okay. Now, if we generate a representation for, let's say, an image of a cat, the cat's image would be somewhere, right? So the cat's image, in fact, would be closer to probably the dog and horse compared to auto. And you can know from nearby words what could be the right words that should be tagged to this image. Okay, so if you did not know that this image is of a cat, you would now know that, hey, because this image's representation is close to the representation of the word cat, maybe cat is the right tag for that. Okay, and this was not there while training. So while training, you only had auto, horse, dog as pairs of each other. Of course, you had the words. Maybe you had the words also, but they're not paired to any images. Some other words like truck and cat. Okay, so so the previous picture was an illustration. Here is actually a picture for, I think this is for a collection of, I think this may be CIFAR 10, but so you have these images represented using all these colorful dots here, and then you have the word representations. Okay, so here we are just again looking at the low dimensional TSNE plot, and we are seeing that the images for dog, so the representation for dog and the word dog, and the cat, cat, which is a new word, they are in the same region. Okay. Okay, so let me summarize what we did in this last section. Okay, because we have only kind of motivated at a kind of a higher level how the embeddings could have, what is the need for such embeddings, like what's the motivation. We want word representations to have similar representations for words which appear in semantically similar contexts. Okay, that was the hypothesis. So that cat and dog will have similar vectors compared to cat and airplane, for example. After that, we said, hey, there's a counting based approach where you just count how many similar contexts a pair of words appear and then maybe do a dimensional reduction there. But we didn't pursue that. We said, okay, maybe prediction based approach can also give us these representations that we care about. And we saw an example prediction task where for a valid sequence of words, we'll say it's valid. And for an invalid sequence of words that we create, we'll say it's invalid. And when we train that, we may get representations for words which will satisfy the property that we care about, right? So which is a semantic similarity. So, and then we said, so that was an illustrative auxiliary prediction task. And in general, there could be many different such tasks. And next class, we'll look at one of these ways of creating embeddings. And we'll also see how to easily get them from packages like GenSim or even TOSH-text and so on. What we did is then said, hey, if you have an embedding, if you have these word representations, how do you kind of gain confidence that they are doing well? So you can typically you'll do dimensional reduction like TSNE, or you can look at nearest neighbors of some example words to get a sense of are the embeddings good enough or not. Okay, and then the last few minutes, we were just discussing, hey, it's not just word embeddings. It's not just the use of word embeddings in unrelated tasks once you get these embeddings, but you can also get these word embeddings while doing other embeddings as well. For example, you can embed words from two different languages at the same time so that you can get pairs of words that you did not know were related to each other. Now you know that they're related to each other. Not just embed two different words, languages, but you can also embed words as well as images at the same time, so that for new images, you can get related words for images that you did not know the words for, and so on. Okay, so that's what we covered today. In the next lecture, we will, of course, talk about sequential models. So the question that was asked early on about how do I go from language to language, like one language to another language, what is it called? Machine translation. We'll look at models underlying that. But before that, we'll look at Word2Vec as a specific example of what is the prediction task and why do I get these word representations which are semantically relevant. Okay, so we'll do that in the at the beginning of next lecture, Word2Vec, and the second part of next lecture we'll look at popular what are called recurrent models. So LSTM is an example model there, so we'll look at that. I think we're out of time, but if folks have questions, please stay on and we can discuss. And otherwise, thanks.